Okay, hello everyone. Welcome back to our episode 19 of the series. For today's video, we will be talking about sum of four squares. According to this chapter, all of the number could be represented as sum of four different squares, in which some of the squares could be 0 or 1. And let's jump into the problems. So express those numbers in sum of the four squares. Okay, so like the way that the chapter did it is just for proving the existence of such an expression, but it's not really that practical to use it when we finding the representation of sum of the four squares, because it involves too many calculations, and it's just easier to just brute force and try to find it. So those are the answers for the first two questions. And question number 3, from this, find the representation of this to be sum of the four squares. So if you pay attention to this chapter here, there's a property to reduce the power of 2 here. And by using this over here, and we get a representation of sum of four squares. And question 4, from this and lemma 1, find a representation of this as sum of the four squares. So we just need to combine 7 and 53 together and get a sum of the four squares by using here, this formula here. It's extremely long, and this should be the answers. And we don't even need to care about this power to 3, because we can just take this square of 7 out and then multiply it. So like we could just multiply the 7 here. Like I'm just kind of lazy, so no, like to be exact, I forgot to do it. Sorry guys. And question 5, use the idea proof of lemma 2 to find the solution of this. Okay, so well, the whole idea is that we will have one more residual than the numbers of unique residuals. Therefore, there should be a pair of residuals that's equal to each other's. So in this case, we sub in the value of 17 and we test all of the residuals of these numbers, and we got this, and indeed we find 15 and 15 here, and yeah, 15 corresponding to 7 to the power of 2, which means x equals to 7 is the solution. In question 6, use the proof of lemma 4, apply this to get a similar smaller multiple of 197 as sum of four squares. So first we're gonna find was it congruent to the modulo. Okay, the modulo is going to be, how many? 8 times 197. So, and the range of the modulos is k over 2 is greater than negative k over 2, but less than k over positive k over 2. So, and after we did that, and we calculate the sum of those numbers here, and yeah, we apply this to the lemma 1, yes, and we get this, and each number should be a multiple of 43, and we divide that and we got this expressions. And question 7, if 8 is a divisor of these, show that x, y, z, w, they are both even. They are all even. One thing we need to know is that we're gonna take a look at the modulo 8, and there's really only one possibility here, is that all of the even square is congruent to 1 modulo 8. And yeah, we can't have any square congruent to 1 over here, because like even if we make them all equals to 1, it is not enough to get into the next multiple of 8. Therefore, they must be all equals to 0. And question 8. If n equals to this thing, show that by suitable ordering and choices of sign, we can get x plus y plus z is the multiple of 3. Well, this question, suitable ordering is that we can pick any numbers from here. And the changing of sign is that we can change x, y, z to the opposite version. Okay, there's 1, 2, 3 different cases. And those cases are going to be different based on how many numbers are congruent to 0. Suppose there are 4 or 3, we pick 3 numbers that sums to 0. If there's 1 or 2 square congruent to 0, we're gonna pick 1 squares and change it to congruent to 1, and pick another square to make it congruent to 2, and pick a 0 at the end. We're gonna get a sum congruent to 3. If there's no square congruent to 0, then that means all of the square is congruent to 1 or 2, and we can control the sign, and we just make them all congruent to 1, and we're gonna find the sum congruent to 0. And question 9, if n equals to this thing, show that the minimum of this and the maximum of this has a range of this. So yeah, so given the fixed value of the minimum of n, if this is fixed, and to minimize this thing here, we're gonna make them all equals to this minimum value, and the sum of those 4 squares equals to 4a squared. And we take the square root by each side, we get this. And suppose the maximum value is fixed, then to get the minimum value of n, we're gonna make all other values equals to 0. And since we have a maximum of b left, the square equals to b squared. And n is greater than that number, greater or equals to that number. So we take the square, b is less than or equals to 1 to the power of 1 over 2. And similarly, to maximize the sum of the square of x, y, z, w, we're gonna make every number equals to this maximum value. So n is less than or equals to 4b squared, and we take the square root, we get this inequality. Okay, sorry, my bad. I didn't show that in the projector, so. Okay, question 10, final question. Woohoo! So if t is even, there's 2 odd, 1 even squares on the right, or they are, all 3 of them are even. Yeah, so we know that they are both evens are not possible because they don't share any common factors. It should be 2 here, sorry, I'm gonna correct it. Okay, so this is the only possibilities, but well, when we do this, all of the odd squares are congruent to 1, and this even number square is going to congruent to 0. So this thing is going to congruent to 2. Since t is even, so it's congruent to 0 modulo 4. Therefore, those two sides are not congruent to each other. Therefore, this is impossible. And that concludes our section for today. And see you in the next episode. Bye. Okay, let me close this thing here.